Militzer from University of California, Berkeley. He got his PhD from the University of Illinois, Urbana-Champaign. And after that, he spent a couple of years at Lawrence Livermore National Lab. And currently he's professor at UC Berkeley. He has been studying the Earth and planetary science problems using computer simulation techniques. Um, and recently he has studied hydrogen helium mixtures in Jupiter, um, and also rocky planets. And he's going to talk about first principle equation of state database that he has developed for warm dense matter computation. Uh, so thank you for giving this talk, Burkhard.
Well, thank you, Farhad, and welcome everyone to this presentation about the CMEC Center. I would like you to introduce a few concepts we're pursuing at Berkeley, and also tell you a little how it fits into the center. The work will be presented from Felipe Gonzalez, who is in our group currently. There's Jiwei Shuai Zhang, who was in our group, then a postdoc in Livermore, is now a staff member in Rochester. We have also Henry Peterson, who was a summer student. We have Kevin Driver, who was a postdoc with us and now is in Livermore. We still collaborate with him and write joint papers. We have François Seberon. I will be presenting a lot of his results. He went back to his native France, and then he works now for the CEA. And we have two new students, there's Tanya Kovacevic and Rustin Domingos. There are not so many results from both in this talk, but we have highest expectations for both of them. They're funded by the center. And then we have our Livermore colleagues, there's Heather Whitley, Marius Neo, and David Swift, and we wrote joint papers, and I will report results from them today. In the center, we have lots of joint activities. Most closely, we work with Sarah Stewart and Davis, and also with our two colleagues, Raymond John and Roger Falcone, and you will see some results of these things today. So what I will do mostly is talk about matter at extreme conditions, and we do computer simulations for this. And in my group, we either focus on material properties or we actually do planet models. So we've done it most recently for Saturn. It was exciting because the Cassini mission in its final days before it burned up, it flew in between the rings and the planet and measured the gravity field. Indeed, it developed interior models to match the spacecraft data. That was an exciting time. We're still getting new data from the other giant planet mission, which is the Juno mission, and we're working on interior models for those, and they look different. This is an old model, we're just doing this. So in case you want to join our group or the center, if you join the group, you can either work on the material side or on the giant planet modeling side, or at the interface between two. If you're interested in doing experiments, I'm the wrong person to talk to. So I broke the apparatus when I was an undergraduate. They told me I should do theory. So then you have all my other colleagues like Roger or Raymond or anybody in the center you can reach out, please do. And then we will incorporate into the ongoing activity. And I will just give you from a theory side a few recent results today. The matters are really extreme in the center. It's matter for extreme conditions, and extreme, we talk gigabar pressures. So we have 1,000 GPa, that is a terapascal and higher like that, and that scale here, 1,000 GPa. Temperatures are here 10,000 or 100,000, and we're talking about matter in the interiors of stars, not the surface, in the interior. These are adiabats for main sequence stars, and they reach into these conditions. This is the area we study with these computer simulations, and these are recent experiments. So what we often do is we compare with ongoing experiments and see how well we agree, and whether there's anything we're missing in the theoretical predictions. And just from last week, we got another puzzle to worry about. I just want to tell you about it. This is basically, we had nothing to do with this. This is the work by Amy Lazicki and colleagues in Livermore, who basically shocked diamond to 2 terapascals and said diamond is still the dominant phase even after you're compressing it uniaxially. even though all the theory says there's this big new regime of BCA. So this is a puzzle because the experiment and the theory do not agree. This will pave the way for more experiments. So definitely we scratched our head and we're going to do more theory. It's relevant for Felipe's ongoing project right now. The only thing we can bother say right now is that when you ramp compress in one direction, the atoms have to rearrange. There's no way you can, the diamond will eventually, atoms have to rearrange. And then Amy's results predict that they rearrange in the diamond structure, even though it should be BCA. So that's very exciting. There will be more things to come from this. So our colleagues use the biggest compression techniques there are, the old two-stage gas gun, there was an old laser. Now you have the biggest laser on the planet, the National Ignition Facility, and we show some results from this. And there's also the Zendia Z capacitor machine that allows you to compress materials magnetically. So what typically happens is you ran a shock wave into the material. So initially it's at some thermodynamic state and it changes discontinuously into another. And then our experimental colleagues, they measure this shock wave, this velocity, and they measure this, how fast the material has been pushed. So by measuring these two waves, they can infer density and pressure from these conditions, and that's typically plotted here. So theoretically, what we do, we typically prescribe the volume of the simulation and the temperature, derive pressure energy. And we solve these third equation among the Hugoniot equations, and then we predict these curves theoretically. So typically, you compress the material, pressure and density increase, and then it keeps going up, temperature's rising, it's not plotted here. And then typically you end up with a state that's close to fourfold the initial density you start. And when something like sixfold comes up, like it was predicted for hydrogen many years ago, then everybody scratches their head. That typically means that something in the material got excited, like electrons. So this is sort of, you will see lots of those curves. The canonical curve starts somewhere at an initial state and gradually rises towards fourfold and may overshoot a little bit before it comes back. And then if something exciting happens, then you go much further. This is what the experiments will predict. They can reach these conditions for a very short amount of time. And then that is the reason why we theorists calculate these curves, because that is the most direct way to compare with the experimental data. I will walk you through a little bit what we actually do. This is using path-integral Monte Carlo simulations combined with density functional theory. Talk a little about recent results for silicates, then go back to work on plastic, so it's mixtures of carbon and hydrogen, CH, then talk about linear mixing, and then describe our database we put together for everybody to use, and it's on the internet. And then I conclude by saying a few things about the phase diagram of magnesium oxide. So at low temperature, we use density functional theory. There's a little picture here. We have the nuclei. You derive with a large computer code orbitals for these nuclei. And then once you have the orbitals, they provide forces on the nuclei. And once you have the forces, you can solve F equals ma. If you increase temperature in that system, of course, everything will move more quickly, but stable bonds break, but also the electrons step by step get excited, and they can get really, really highly excited. And then we're no longer sure whether the theory is 100% appropriate. There may be fundamental concerns whether this density functional method will work properly, and also practical concerns. If the electrons are too highly excited, the number of orbitals basically explodes. So what do you do in such a case where you have millions of orbitals to consider? And there is actually another technique that works extremely well at high temperature, but it's not using wave functions. It's Feynman's path integral method. And you don't learn about it in your undergraduate physics course because it's sort of not that much taught, and although it should be. The irony is that Feynman developed this to study superfluid helium at 2 Kelvin. And we're using this to study millions of kelvins. So it's really, really good method. And I will show you now. It actually becomes more efficient at higher temperatures. So we have one method at DFT, when you go up in temperature, it becomes harder and harder, and we have another method, particles, that we come down in temperature, and that gets harder and harder. And it's the art of the game is to connect these two things seamlessly to one equation state that allows us to describe matter. So the method particles was developed by the group of David Zeppeli in the 90s, very successfully. It worked for hydrogen, but it didn't work for other elements at the time. So what we do, we extended it to helium, for example, and then we can put these equation state together. So here's DFT, these are the points, then there are the path angle points up here. And at really, really high temperatures, you can actually use an analytic, the biomodel, and you get very good results for these things. Over here, collaboratively with Xu Hu, we basically did the same thing for hydrogen to put together equation state table for inertial confinement fusion experiments. So how does this actually work? What are patterns? And I want to remind you that when you took a StatMech course, you probably learned about the Boltzmann factor that we had certain states, they all got a weight by the Boltzmann factor, weight by the energy. And then there's something like the partition function. Once you know the partition function, all thermodynamic equilibrium properties are determined. So path-integral, we use something very similar to the Boltzmann factor, but it's a density operator. And it's a quantum mechanical operator. Then you can stick two things that has like an R and an R prime. At that moment, everybody is already confused typically. But I can tell you, once you characterize this density operator, you get away with deriving this partition function and these averages that you want to calculate without ever the need to describe every single eigenstate. That's the trick. You get all the averages without explicitly deriving the eigenstates. You can if you want, but it's a way to get around this. This is why the density matrix becomes very, very useful. So what you do is you break this operator into a product of many of those things. And that seems to, maybe it makes it harder, but not really, because if you divide it up into so many, many small steps, you can characterize every step. And it's called a step because in quantum mechanics, you may have remembered, sometimes you insert these complete set of states, we integrate over all intermediate positions. And if you do this repeatedly, it's basically like you start at R, you end up at R prime, but it becomes a stepwise process. You step through all space and you have to integrate over all intermediate steps. You have to prove an integration over all possible paths. And the way why this is useful is because every step is better characterized than the original problem. So you're trading one problem for the other, but with computers, you can actually integrate over all those paths in a Monte Carlo fashion. You just need to know, you sort the good ones from the bad ones. And there's this term that is the action that tells you what is a likely path, and if it has a low action, it's a very likely path. Has a high action, then it's basically an unlikely path. And what you have to do is to integrate over all those paths. So all possible ways from A to B. That is a path integral. It may not be so familiar because it's not using wave functions, although you get the same answer here. But some of you may have heard this process where you go through all possible points at once. In principle, you have to integrate over all possible paths in the universe. The particles can travel everywhere. If that sounds familiar, then you probably read Douglas Adams. The infinite improbability drive is just the practical implementation of the path-integral method. So we actually use it on the computer. They actually have made a lot of money with it. That's also a good way to proceed. So nevertheless, Douglas Adams and all the other people did not tell us how to do fermions. So that is a challenge for density functional method, but also for us. It's very difficult to solve it. We have to restrict these paths. That makes the method no longer exact. And we have special methods to restrict the path in a qualified way that we actually solve a fermionic problem. If we don't, all matter would collapse. But nevertheless, this is where our energy goes. Sometimes if you have to take it all apart and look what happens deep inside your code, this happens. This is most likely where this is coming from. So let me talk a little about the applications now. We have silicates and we want to compare with experiments. So here are recent experiments by Maurice Millot. They also measure temperature and pressure. These are the data points with error bars. And the density functional calculations that were performed agree reasonably well. At least we're on the 1 sigma error bar for these calculations. So that is an example where even with temperature measurements, we agree quite well. Then we take the same simulations and apply it into much broader regime and temperature, lots of points, put it on a supercomputer, basically derive these GFT calculations. And then at higher temperatures, where they are no longer practical, we use path angles. So these are all the points that we derive, and this is a typical shock-Hugoniot curve that we derive. So we can predict what should happen in such a shock rate experiments, worked by Felipe Gonzalez, and it was published last year. So what can we say? Well, we predict there's a gradual rise in the shock compression. And then you reach a point where two curves diverge. This is a curve that was calculated without exciting the electrons. So you keep electrons in their K shell and their L shell. These are the first shell and second shell electrons. You just say we don't want them to be excited. If that were true, then you would follow this curve gradually up to this fourfold compression. However, real materials, electrons can get excited, and you scoot over. The material becomes more compressible because there's energy that goes into exciting these electrons, and there is a result, the material under these shock conditions becomes more compressible. So this is the real curve we calculated. This blue shaded area measures the effect when the L shell electrons get excited. Then you exceed the fourfold compression regime because a second process steps in, and that is the excitation of the K shell electrons. So at that moment, we're moving K shell electrons from the cores of oxygen and magnesium. If you're going up here in this regime of 10 to the 5 GPa, then you start removing, stripping also the last electrons of your silicon nuclei. So this is how you can read this graph. Here we freeze the 1s state in the nuclei. That's this curve. And this additional compression is the result of the K shell or 1s electrons being lifted out of their potential wells. And this gives you this additional compression. You go higher, then the effects of relativistic electrons start to matter. That shifts the curve a little bit away from this fourfold regime, and it will keep going, keep increasing here. And then there are also radiative effects. These conditions matter by itself, will start to radiate in just Planck radiation in simplest terms. And then that radiation becomes so abundant and so powerful that it actually makes an important contribution to the pressure, and that contributes to the stability of stars. So taking the same technology and now switching back to CH plastic, where we actually have experiments that reach the regime of K-shell ionization. So CH is important because it is a coding material for hydrogen or ultimately deuterium-tritium mixtures that are the basis of fusion experiments. So it's this shell here with a few other layers where X-rays that hit the whole round and then would bounce off, and then these X-rays will compress this fuel capsule, and if it's done nicely and this really shrinks by a factor of 40, then you may actually reach a fusion condition, although it hasn't been reached yet. So here, for that reason, we want to understand how does plastic behave under shock conditions. It becomes an important material just for this technology alone. So we've done this a couple of years ago. It was led by Shuai Zheng. We got a lot of computer time at the Blue Water Supercomputing Center in Illinois at the time. And we repeated these steps, combining DFT with path angle and then calculating these shock-Hugoniot curves. This was the state of the art before we put our results on top. These are different experiments. Many of them have large error bars. So when they're so large, then they're not very constraining for our theoretical predictions. Then we have different equation of state models. Here's LUS, for example, that's quite compressible. Here is the Purgatorio curve put together by colleagues at Livermore. Here is the orbital free density functional calculation by Su Xing. That is this is an approximate way of dealing with density functional theory. It's really good at high temperature, but it doesn't capture shell effects very nicely. So the K and L shell ionization, the model doesn't, or the theory doesn't make a very good description of these different electronic shells, as we'll see. So we put our results on top of this. So this was what Schwai published. We see a little shoulder here with the L shell electrons, and then you have the shoulder here, and then here we have the K shell ionization. So L shell is predominantly here in this regime, and K shell really, really takes us far out here, almost as far as LUS had predicted. We see some discrepancy here, and that's basically the transition issue from the L shell to the K shell. So second shell of carbon being ionized, and this is the first shell of carbon being ionized, and that dominates the compression, which is almost 4.7 at these conditions. So now experiments were published. The first one was actually Thilo Döckner, and he probed conditions not quite in the gigabar regime yet, and they are still in the regime where we studied with DFT. We got a very good agreement with a DFT calculation. We see a little bit of a departure here as the L shell ionization is almost complete, but nevertheless, within the one, we're dead on. This is as good as we probably can get it from between an agreement between theory and experiment. The second experiment was just published in Nature late last year. That was by Annie Creature. They reached the gigabar regime. Gigabar is up here, they're very close to it, and these are their findings. So the agreement is not quite as good. So we are within the 1 sigma error bars, but there's a little bit of an offset between theory and experiment. So we see as we reach the end of this L shell and K shell ionization, we see the shoulder, and Annie sees a little bit of a shift compared to Thilo Döckner's results, but it's probably possible to draw a smooth curve through these things, and we have one of those plausible ones is here. And keep in mind, these are the most advanced experiments exist. This is a spherical converging shock wave where you have to measure density and opacity changes simultaneously. It's something very difficult to analyze, and people are still improving that technique, understanding this process better. But at least for the first time, we reached the gigabar regime. That is a significant accomplishment by the Livermore team. So we have other results produced at NIF that Schwai published in collaboration with other people at Livermore and also with our group. And what we've done is we calculated the DFT results and then combined them with path niggles and calculated these who go in your curves. Here are the experimental results. And we get very good agreement with the theory. So similarly here, we have cubic boron nitride, it's B4C, and the agreement, it's remarkable how well the theoretical calculations agree with those two sets of measurements. And then we did something very simple. And we basically overlaid the results with a simplified simulation method. And these are the blue curves. And we did something slightly ludicrous. We basically said, can I get those results from fully interacting simulations of boron nitride and boron carbide by pretending, or rather combining the equations of state for boron and nitrogen separately, and with boron and carbon separately, and try to get the same result. And we basically got a really, really good agreement. So we basically have this linear mixing approach where you mix two equations of state, and we almost can reproduce these experiments. So someone in the chemistry community would say, ouch, this possibly can't work. So, and what basically happens is you have a fully interacting compound. Here the example is MgO, where all the magnesium and the oxygen atoms fully interact with each other. You derive pressure and energy. And on the other side, someone comes along and says, I have a really, really good equation say for magnesium by itself. Everything is interacting with everything. And I have another set of simulations where I have oxygen by itself, and all the oxygen atoms are interacting with each other. And then you're saying, well, you're adding the two volumes together according to their molar fractions. Then you basically adding all the internal energies at the same pressure and temperature. And then you derive the density this way. So this is linear mixing, sometimes also called additive Wald. So what you're assuming here is that a magnesium ion or atom doesn't care whether it's surrounded by a mixture of other magnesium and oxygen atoms. And the oxygen atoms similarly don't care, but it's basically surrounded by atoms of its own type only. Well, the chemists would say, obviously this can't work because you're missing all the chemical bonds. And I agree. In a regime where chemical bonds are important, this will not work. But as I will show, at this high compression state where everything is a plasma, this is a really good approximation. So we've done this here now, not just for boron compounds. We actually tried this for magnesium oxide. And we also tried it for MgSO3. These are all fully interacting Hugoniot curves compared with experiments. Here they compared with Marius Mu's GRL results. It looks really, really good, fully interacting. So now we try the same thing. We didn't have a fully interacting equation. We only had one for magnesium, another one for silicon, another one for oxygen. But all of those three were derived with a high precision first principles calculation. So we're not compromising on the underlying equation state. You're compromising by neglecting the reactions and ask the questions, where does it work and where does it go wrong? And what we find here is the following. We see that for magnesium, it basically works, magnesium oxide, it works very well in this K-shell ionization. And we see deviation around 3.2, where the temperature is around 200,000 Kelvin. So above, at these really extreme conditions, chemical bonds are not important. And we get away with this linear mixing approach. And similarly here for MgSO3, we have the chance to calculate these Hugoniot curves at just mixing the element abundances. There are small deviations here that relate to the ionization, and maybe they're real, or maybe they are the fact that the equation state tables by itself may not be perfect. That's still not fully out, but overall, it works remarkable. You get such a simple calculation. And I tell you why this is important. If you have to repeat a bona fide, fully complex Hugoniot calculation for every material that has two types of atoms, that's an n squared problem. N is the number of elements. If you get away with linear mixing, it's an n problem. You just have a table for every different element. That's an n, just scales from the number of n. While if you have to study every mixture, it's n squared or n cubed, if you like. So if linear mixing works, that makes someone's life a whole lot easier. So it's really good that it does for these extreme conditions. So that was a remarkable discovery. We shared it with, we wrote a joint paper with our Livermore colleagues to tell the world about it, that these Hugoniot curves are actually can be calculated with the linear mixing approximation, even though we wouldn't expect it. And the reason we quantified how big the error is, and the error is there, but it's so hard to move the Hugoniot curves around that the linear mixing error is actually small. So that's why it works. So this is the joint paper we published last year based on this. So then we just looked, well, if it works so well, how about we just apply it to a few more materials? Because we have a carbon equation state here for oxygen. How about we do CO2? And that was right at the time when colleagues at Crandall out of Rochester would actually publish their PRL. So the highest points here we can reproduce very well with our linear mixing approach, because we already had carbon and oxygen equation state tables. It took us a day, or took us an hour basically, to gather these results. Otherwise it would take 6 months, and it takes a specialist. So we've done this for water. Here are our colleagues who've done this for fully interacting water, and this is us. We just calculated equation state table for hydrogen and oxygen, and we combined them, and this is basically the results from Podorets, and this was corrected by Marcus Knudsen. We get really, really good agreement. So apparently, this linear mixing approach is actually quite useful. It simplifies things. And then we basically said, well, if it works that well, how about we make it accessible to the world? So we went back quite a way, and we took equation of state tables for more than 20 papers we published, put them all in one big table, and put the table and the interpolation code in the inlet. That's what you see here. The work's published in PRE, and it allows you with a few clicks of a button to have access to these 5,000 first principles calculations. So you get fully interacting material if results if you're interested in the material that we happen to study. And then if you don't have this, then you have to go back to linear mixing. Then you get a result at high enough temperature. So you should go and download this code. It's a good equation state code. It's C++, and it's C++ calls Python, and then it makes nice graphics. And this is all on your computer with a few buttons. And this was published earlier this year. And we already have one really good use for it. Didier Soumong, he is the leader of a gigabar experiment. He assembled a large team to make this happen, to use the NIF, National Ignition Facility, to study conditions on white dwarf stars, in particular carbon and oxygen mixtures. And Roger Falcone and his colleagues at Livermore and many others to make it happen. But basically, we're proposing just let's use this big machine to say something about the extreme conditions in the star for carbon and oxygen. And the first thing, there approximately have one-to-one mixtures, you want to have carbon monoxide in there. And they said, we don't want carbon monoxide. It's not because it's poisonous, but it's probably more the fact you have to freeze it and start to shock under cryogenic conditions, and that was hard. They basically said, isn't there something else you could use to get the same physics out? And there is acetic acid that has this one-to-one carbon-oxygen ratio with a few hydrogen in it. Then there's a glyoxal, which is carbon-oxygen plus a little bit of hydrogen in it. And we just wondered, is that something we could use? Would we get the same conditions out of this? And Didier said, well, Burkhard, you just made this first principle equation state. You should just basically be able to calculate this very quickly. And I told him, sure enough, it would be much better if you would be able to calculate. So Didier became the first bona fide user. And he calculated these curves here. I've literally put this graph here that he put together, and he compared this the resulting shock Hugoniot curves with that of diamond and oxygen. And all he had to do is to compile the database and then put these lines here. And that the code would bring up graphics and write data files that predict the shock conditions for acetic acid and glyoxal by combining oxygen with results in the database for CH. That was cool. That was great. It would have taken us 6 months to do this before. And now someone else who doesn't run computer simulations on a day-to-day basis can do this within a couple of hours. So to move on, I want to just say a few things about another project at lowered conditions, and that relates to solid and liquid silicates. And the results were also published last year. And it started with a conversation at AGU with Dwayne Fratanduno in the hallway. Unfortunately, these things you can't have right now. But that was actually conceived when you still could. We had simulations for this, and Dwayne had shock results. And he sort of asked us whether we thought silicates are insulators for semiconductors. And we said, sure, look at the Earth. Electrical conductivity cannot be conducted. Otherwise, there could be a magnetic field. The mantle doesn't do that. The magnetic field on the Earth comes from the iron core. So therefore, it's a good indication, not just theory says, that silicates are insulating materials. And then so Dwayne was sort of pushed and said, well, can you just double check? Make sure you double check the solid and the liquid. And then you go home and you check your results. And it's wow. So basically, if you look at the solid state, there's a small band gap of 2 eV. That basically means if you want to excite electrons, there are no states, there's a gap, missing states, which means you have to excite energy to go across this that gap of 2 eV, and that's 20,000 kelvin. So normally it doesn't happen. So that requires energy, therefore these are poor conductors. It can happen semiconductor, you can have some of these excitations if you go to high enough temperatures, but nevertheless, if the material is solid, there is this gap, which makes these things poor conductors. However, what we didn't realize till someone prompted us to investigate it, if the material melts, the system gets disordered, all the atoms now have a slightly different environment. That silicon ion is different from that one. And therefore, its localized states get deformed. And then where there were no states before, the deformation of the electronic structure fills in this gap. All of a sudden, there are states, what was formerly a gap. So you have a gap here. Now it's much easier to excite electrons because there are states. You don't have to jump over this gap. And that makes the material electric conducting. It's not a great conductor. There's still this trove here where there are not that many states. A good metal would just be a straight line here where I have a constant number of states. This is the density of states here. And but nevertheless, the gap got filled in. That means that all of those three materials become core conductors. And that was Francois did it extremely carefully. He went through the literature and analyzed what that means. And it basically means that magma oceans that were existed for the early Earth and for super Earth planet, they may exist much, much longer. They can generate a magnetic field. So you can have tectonic plates that sit on top, and still you can have a partial magma ocean. We know this happened in the early Earth, and with our good work by Labrosse and colleague that showed us it crystallized from the middle up. And what this work here showed is basically that for the super Earth ion-free systems, you get conditions where this conductivity is high and viscosity is moderate, so that you get a state that can generate a magnetic field. So that idea was taken on by Lars Stigsrud. He published a nice other paper where he actually focused on conditions for the Earth and showed that it is the same mechanism applies, and that it's basically, even for the early Earth, if you add a little bit of iron, you get a state that where the mantle can generate a magnetic field. And that may help us to understand why we get very early, we have rock samples that show a mechanization. So coming to the final topic of this talk, we now want to take one of those materials, magnesium oxide, and review what has our experimental colleagues predicted for its shock conditions. See, these are different shock experiments by two groups. One is Stuart McWilliams, the other one is by Bowley's. And they probe these high temperature measurements here with Hugoniot curves and mapped out the whole curve with decaying shock experiments. And these states up here around 10,000 or 20,000 Kelvin, they are liquid states. So there's no ambiguity about this. What's the exciting part now, as they were coming down in temperature, they found this big excursion. So Stuart found this big change, a huge change, and that translates actually, as we'll see, in the big change in density. So something changed drastically as you approach the solid. And then similarly, Bowley's had very compatible results and found it at slightly different conditions, and then switched also to a state that's most likely solid. So you could argue this is a solid liquid transition, but you could also argue different. You can say this has something to do with the B1 to B2 transitions, because magnesium oxide is theoretically predicted to change from a sodium chloride structure to a cesium chloride structure because it forms slightly more densely packed. That's not been seen directly in diamond andesite experiments because this happens around 450 GPa, which is a little bit outside the regime where it can be accessed. So it's at this moment, it's a purely theoretical construct. So therefore, the two groups chose to interpret their findings differently. One group said it's a B1, B2 effect, and the other one basically says it's a melting transition that leaves rise to this change. So this is a good playing field for theorists to be relevant. We'll see what we can say about it. And Francois, that was his sort of a perfect project for him to take on. So, the first thing he calculated were these Hugoniot curves. So this is his liquid branch. It's not in very good agreement. It's outside or marginally within the one sigma error bars. That is definitely not perfect. Here, it's also temperature. So it's not the temperature measurements under certain conditions are difficult. So maybe it's reasonable that the agreement isn't so good. Nevertheless, this is an open question. Then he calculated the B2 branch that's shown here. And there is only a small offset compared to the B1 branch. And that is related to the change in density. It can shift, the Carbonic curve can, at least in equilibrium, jump from one phase to the next. That's basically if you apply a thermal equilibrium, it would gradually march along the phase boundary, have a mixed phase here. And how far these two branches are offset depends on the density contrast. So that's small between B1 and B2 and large between a liquid and B2. So therefore, that big change that our experimental colleagues have shown here must be related to melting. It may not, melting may not be the only thing, but it must be involved. That's the only thing we can probably say with certainty, because this is a small offset. B1, B2 will not cut it by itself. So Francois went on, and the work was published in PRL last year. He calculated these phase boundaries with density functional molecular calculations that also use thermodynamic integration to obtain Gibbs free energies. So that's hard. It included the enharmonic part. So this curve is basically derived with enharmonic calculations. The harmonic results are a little shallower. They would predict a much larger B2 regime. Well, if you include the enharmonicity, that stabilizes the B1 phase regime. And that's why he gets this jump at relatively high temperature from B1 to B2. And then he also calculated the melting rates for both phases. Error bars are large because it's not a simple calculation. And nevertheless, this is the phase diagram for the first time with density functional theory that includes the enharmonic effects. This is final result. And this is the phase diagram that we propose. So therefore, we suggest that melting is involved, and also your curve goes for a little bit to the B2 phase if the experiments have actually time to crystallize a generated B2 phase. Well, from Amy Lazikou's result, now that is all a big concern. So I'm sorry, Amy, you're making it much harder for everyone. Congratulations, you give us more work to do. So this is nevertheless, if you assume equilibrium, these are the results that you obtain based on Francois' work. So I hope I used that time efficiently to tell you about path angles, tell you about our equations of state, tell you about silicates, our comparison with experiments, and then convinced you at least that linear mixing is something that is useful as long as the temperature is high and you're basically 3.2-fold compressed. If you're interested in doing equation state work, maybe you're going to give it a shot and download our database. And these are results for MGR. With that, I stop and take questions. Thank you very much.
Thank you so much, Burkhard. Appreciate it for an excellent talk. This talk is open to question. Actually, we already have a few questions in chat. So please type your questions in chat. Let me read the first question. That is, do the CH results assume that the carbon and hydrogen remain fully mixed?
Yes, and we tested both things. So we the calculations I presented here, they're fully interacting, fully mixed. We do not, fully mixed. We do not see any phase separation. We do not see under these conditions the diamond forms, because that has been seen in other experiments. But the temperatures that we were interested in were just too high, for instance. So this is a regime that would happen at below 10,000 Kelvin, where we're looking at higher temperatures. That may be one way to answer. The other way to answer, yes, the results I presented were computed with a fully interacting mixture, and but you get very similar results if you use linear mixing, where you take the carbon, the hydrogen equation. So that's actually in the paper. Yes.
Okay, thank you. The next question is the same statement, I think, not to mixing, The same statement can be made even in a regime where chemical bonds are important as long as the species captured the most important contributions, for example, NH3 plus water as a linear mixture.
Yes, that is true. We were not pursuing this regime because this is so extreme conditions we're interested in, that this is not a good approach because these species don't exist there. But nevertheless, the person is correct. If you have well-defined chemical compounds and the physics is determined by their bonding, then the same effect certainly happens. But we also got colleagues from Los Alamos who basically said, no, this does not work. And they were right, in certain conditions it does not work at low temperatures, but we at high temperatures actually it does.
Okay, great. There are a few more questions. What is the outlook for extracting other quantities or observables from these calculations, for example, conductivities?
So that is something that's not in the database, and that's something that requires more work. So we've not pursued it for different reasons. One is we've never succeeded to extract conductivity calculations from pathogens. So that is you have to be really, really smart and to do some big rotation of these imaginary time path angles. That's something we're still waiting for a really, really, really smart grad student to do for us. And then for the DFT, in principle, it works. We've not invested in this. That's something we should actually do in the future because that's measured in the experiments. We have neglected this a little bit so far.
Okay, great. Thanks. And they are also saying wonderful talk. And the next question is, thanks for the great talk. Could you please say more about why adiabatic are used for planetary modeling? Surely there is a heat generation associated, for example, crystallization, radioactive decay, gravitational contraction, etc. I think there's a correction, adiabats.
Yes, so that is we have a simple answer that is probably 90% correct and 10% wrong. So let me just say the simple answer. If you drill a hole in the earth and you measure actually heat flux, you can actually see it in the earth. It just has a very sluggishly convecting. The adiabatic approach is quite reasonable. If you go to Jupiter, there was a drop was probed into it. It only went up to 22 bars before it burned up. But for those 22 bars, it measured an adiabatic profile. So that's good evidence that this actually is a smart approximation. And the reason is that planets cool, and the only way heat gets out is through convection. So radiative processes are negligible and conduction is not efficient. So the only way planets cool is through convection. And then you bring up material that's hot in the interior, and then you bring it up in an adiabatic process. For that reason, that is a good approximation. And then there are problems with it. For example, if we look at the Earth core, there is a boundary between the mantle and the core, and there's this boundary layer where that is not adiabatic. You have this rise in temperature that makes the core much hotter. That's the case where it's not. But for the other part, it's a reasonably good approximation because planets cool convectively, and that makes it adiabatic. But that's certainly an approximation.
Okay, the next question is related to the conductivity question, and I'm rephrasing. I apologize if I do it wrongly. So can you also extract optical properties, for example, opacity?
So that I'm not the specialist on this. This is yet harder because as far as I can tell, directly from ab initio simulations, we have a many-body system in high pressure. I don't think anybody has ever calculated opacities. And then probably someone will tell me that I'm wrong, but at least I'm not aware. This is definitely very hard because you have to have bound, and bound free, and by free transitions. And there's so many of them, and that's challenging to put in context with density functional. So typically people do these calculations rely on simpler approaches where not everything is a fully self-consistent density functional calculation that's been done. So this could be done. And I know Sushing who works on this. I know people in France are working on this. There is progress to be made. And by the moment it has not been done. So yes, that is something for the next 10 years to do.
Okay, great. Let's move on to the next question. Would the best experimental test of these models be at maximum density plus minimum temperature?
That depends on the application. So I would say my other half really wants to know something about planets. And planets are basically close to adiabatic, which we just discussed. And therefore, adiabats are much shallower curves than Shikoku-Goniya curves. There's this big discrepancy in temperature. So therefore, if you want to say something about planets, then these gradual REM compression experiments are much more useful. But if you want to say something, want to test the theory, whether it's right or wrong, what you really need is an experiment with very small error bars. That's more important to the condition you actually get. So at the moment, from the CH experiments, the target was we really are the first one to get these extreme conditions. And I suspect that the team will actually go back to scale back a little bit and focus on making these measurements more precise. So that will certainly be a trend. So yes, precision over exceedingly extreme conditions, and lower temperatures good for planets, yes.
So thank you. Let's move on to the next two queries. How can we include temperature variation effect in DFT? That's one. Second, which atomic process does this follow during high compression or high pressure regime?
So radiative processes, this is not my expertise. And when sometimes we add these little corrections for the radiative term, this is done very, very simply after the fact. Transport or radiative transport in extreme conditions is a challenging subject. So there are many, many groups working on this. I can't really answer how they approach this, but its principle, it's the same argument. You try to capture all the relevant processes. How do photons excited and captured? And in principle, that information is available in density functional theory with a few caveats. This is a mean field theory. We don't have a fully many-body you have single particle states and not represent the many-body physics. So you have to do better than density functional theory, and that's hard. So for that reason, so that's the main problem. Density functional theory may not be good enough because the single particle theory, and it's not clear how to extend it. But people are definitely working on it, and national labs need good people to continue their opacity work, yes.
Thank you. And the last question on the chat is, what is the source of error for Goniya experiments? Is it from instrument or physical properties like conduction?
So that is, of course, I'm the wrong person to ask. There are things that are difficult to control in the experiment. For example, you drive it with a laser, the laser hits some layer that will then mitigate the shock. But whether the laser hits first, it will generate X-rays, and the X-rays can, if they're not properly shielded, they can preheat the sample. So that is a typical uncertainty in the experiments, to what degree a preheat is prevented. Then the main challenge in the experiments, and that would really make an impact for planetary science, is the temperature. The temperatures are very, very difficult to measure under shock conditions, because you may only get a Planck spectrum, and then you can fit it with a large uncertainty what the temperature will be. Sometimes you can't even measure that directly. There are conditions, if you reach conditions where all of a sudden nuclear reactions will happen, you get a really good temperature measurement, just because they wouldn't happen otherwise. But in general, the temperature measurement is the main difficulty for the experiment. That would make a big impact for planetary science if this could be made more precise. And then the other uncertainty are controllable things like what density and what pressure you can infer. And that has been done before. It's still very difficult, but it is still a certain source of uncertainty.
Okay, thank you. So I would like to suggest, Burkhard, maybe if you can stay for another 5 or 10 minutes in case someone else has a question. And if small group would like to stay and talk to you. So before we do, I'd like to thank you again for an excellent talk. It generated significant discussion here. So appreciate for your time. And some of you, if you like to stay and ask question, Burkhard will be here for another 5 to 10 minutes.